Hi, in the digital electronics industry nowadays, there are at least four types of tests need to be done on our devices. First is parametric test. Second is functional test. Third is timing test. And the last one is the state machine verification. However, at intermediate level undergraduate courses on digital electronics design, three of those tests are beyond the scope. The parametric test, for example, is for analog courses, and the timing test, on the other hand, is done at least at final year project or graduate level. And the state machine verification is normally done in the industry only. So for this assignment, we will do functional test bench. There is no standard way to do any test bench. In this assignment, however, we will try to make the process more systematic and looks more automated. We will also write the test bench using only Verilog statements that we have learned, that some more advanced coder should know that there are much better ways to write the same code. Get this document from your instructor, then let us read through. The simulations that you have been doing with quarters 2 or model sim are already a kind of very simple test bench. The idea of test bench originates from the real electronics testing table. It is just another HDL module that drives inputs to another module and reads the outputs. And if the test bench is testing for the correctness of the output of the module, meaning the functionality, then we call it a functional test bench. The following are some general components of a test bench to make it more systematic. First is an input clock to drive the test bench itself. This clock will be divided so that the MUT can be driven with inputs at slower rate. Next is the strobe signal to allow us to monitor the output of MUT only at predefined times. It is generated during the clock dividing process at the second last pulse. This is to allow the MUT to produce a valid output while avoiding glitches into the next clock cycle. There will be a state machine in the test bench to synchronize and time the forcing of inputs and capturing of outputs. This includes a calibration phase where comparisons are done on correct and incorrect output. Calibration is to ensure that the test bench itself is reliable. Next is a list of input values to be fed into the MUT called input vector. We will also need input vector to be compared with the actual output from MUT. There will also be a comparator, either equality, inequality, magnitude or others, to compare output vector and MUT output, whose output is to be gathered by the strobe to the observer. Finally, this is the conceptual schematic diagram for the test bench that we just explained. Specifically for this assignment, we reduce the above general scheme into something as follows. First, we set the clock to a 1 millisecond clock. Next, the clock would be divided by 4, meaning the strobe is generated at the third clock. Then the state machine for the test bench will just be counting the clock pulses and issues out the input and output vectors according to the count. The data size of the operands and the result will all be fixed to 6 bits only. The comparator, on the other hand, will be giving a high signal if the result of MUT and the output vector are different. This is equivalent to an XOR gate. And lastly, since the MUT is pure combinational, then there is no need for a clock for it. After considering these reductions, this is how the schematic diagram will look like. Let us now start with the coding of the MUT. In this example, we will do a subtractor as the MUT. You need to find your own assignment of calculation given to you for the MUT. As you can see here, the bit sizes are all 6-bit for the operands and the result. Make the module pure combinational by using an assign keyword. Now we write the code for the test bench. We start with the clock and the strobe generator. Since we want to divide the clock by 4, counting with a 2-bit register is enough. The divided by 4 clock for the MUT can be obtained from its MSB. The strobe is then generated at the second last clock, which is when the clock counter bit 1 is 1 and the bit 0 is 0. If you simulate this code now, you will see something like this. Notice that the strobe is positioned at the third clock in groups of 4. Next, we code the test bench FSM to issue out the input and output vector. We need a counter to time out our sending out of input and output vectors. This counter will be driven by the same clock that drives the MUT. We will have a few blocks of if-else that issue out the vectors when certain counts are reached. In this case, I choose to issue the calibration vector for a correct case at count of 5, then the calibration vector for a wrong case at count of 10. Then the actual 4 tests I did at 4 count stops that I choose. Be sure to always assign the same set of output registers in every if-else block, regardless of the block's purpose. The second last block is where we stop the counting by giving the counter the same value, and of course the vectors are also given the same values too. The last block is the block where we handle the counts that don't match any of the counts for the above blocks. This block is where we just push the counter further, but we keep the vector's value. Done that correctly, you will get this simulation result with all counting and vectors out. Next, we instantiate the MUT. This is where the tested calculation is done. The operands of the MUT will get the input vectors, and the result from the MUT will be wired out to the next stage. This simulation shows the input vectors and the MUT result during the calibration. Next is to compare the result with the output vector. We do the comparison with bitwise XOR gates. If the MUT result and the output vector are different, there will be at least one bitwise XOR that will result in a logic 1. This is equivalent to a boolean true. Then we give out a 1 because we want to signify the difference as error. Otherwise, if the MUT result and the output vector are the same, all bitwise OR will result in logic 0. This is equivalent to a boolean false. Then we give out a 0 because when the MUT result and the output vector are the same, it means our calculation is correct. The simulation of the comparison process shows that it gives 0 for all tests and calibration of the correct pair, but a 1 at the error calibration as expected. The final code is to strobe the comparison result. The purpose of strobing is so that we see only the result when it is stable and clear, not while it was fluctuating. The code is simply an AND gate between the comparison result and the strobe signal. And finally, the simulation shows that the test bench behaves correctly by strobing out pulses of logic high signals when the comparison mismatches. Otherwise, nothing. So that is our simple and rudimentary test bench. Good luck with the assignment.